Okay. So today we'll be covering, I told you, kinetic theory of gas. We are actually not going to the core part of kinetic theory of gases today. So we'll be covering some topics called gas laws, ideal gas equations, all those things we are going to cover. Some problems also we are going to do. Okay. So I'm starting. So I'll be starting with the gas laws. I think all of you know in lower class itself, you know a little bit about, or you already have some experience. You might have experienced the effects of gas laws. So first I will be discussing about Boyles law. Okay. So Boyles law is the relation between pressure. See, before going to that, before going to the gas law, I will give you a little bit introduction about this chapter. So in this chapter, we are mainly discussing the effect, the macroscopic effect. First we will discuss about the macroscopic effect. See, macroscopic in this chapter, in thermodynamics and this chapter, there are two things. One is microscopic and one is macroscopic. Microscopic means, you are looking in molecular level. So the kinetic theory of gas is more in that side, okay, looking close to one particle, what is, how it is moving, we are tracking each particle and trying, that is called statistical approach, and we are trying to find out based on individual particle, based on, we are trying to find out the overall effect. For example, when you are increasing temperature, what is happening to the molecule, what is happening to the speed. So those kind of things, what is happening to an individual molecule, those kind of studies comes under the topic called microscopic, and whereas macroscopic is directly dealing with the overall effect. For example, if you are heating, what is happening to the pressure of the system, or what is happening to the volume of the system. So such studies are called microscopic. So these laws, the gas laws is basically dealing with macroscopic study. So in that, first we are going to discuss about the gas laws. See, you can see here Boyles law. The first law is Boyles law. Okay. So let us see what is Boyles law. So before going to Boyles law, I'll try to explain. I'll try to show you an experiment to visualize Boyles law. Then we will go back to the theory. Okay. So look here. We have a system here. Okay. I have a, just a second. Yeah, wait, please stay online. We are doing some camera arrangements. Let us do that. Okay, so we have a tank here, basically a glass tank. Okay, you can see here a glass tank is there. Inside I have kept a balloon. Okay, balloon with normal air inside. Okay, now this line is, the top is completely sealed and closed, and the top is connected to a vacuum pump. We have a vacuum pump here. Vacuum pump means we are trying to evacuate. See, if you have some volume, if you are connecting a vacuum pump, suction will happen. The vacuum pump have a mechanism to suck out all the air from this region. So this region become vacuum, or we can say that when you are doing that, the pressure is reducing. When you are trying to remove air from the system, from this tank, this is our control volume or our system. See, and in thermodynamics, system means the region of space which we are interested. So that is called a system, thermodynamic system. So in this case, this is actually a system, and from the system we are trying to take the molecules, take the air out. In our case, atmospheric air, gas is the air is there, and we are trying to pump out there. As a result, naturally what happen, if you are taking air from a region, the pressure in that region will go down. So pressure from that region will go down, and as a result, what will happen to the volume? This is very, very interesting experiment. You may not expect this, the result of this experiment you may not expect, but it's very interesting to understand concepts like this. Okay, so let us see what happen if I switch on the pump. So it's like a motor and have a system to continuously remove air from this region. That is what we are going to do. Okay. So here, see, I'm trying to operate this. When I switch, the moment I switch on the pump, you focus on this balloon. Okay, what exactly is happening to the balloon? Okay, let me do that. Just a second. Yeah. Okay. So I'm going to switch on the balloon. All of you, put your left focus on the balloon. Okay. Yeah. All of you see. I'll repeat the experiment once again. I will show you. We can, all of you, carefully understand. Try to understand the concept first, so that your progress in theory will be much easier. So I'm going to switch on the pump. Look at the balloon. can see that the balloon, the size of the balloon increased. Okay. So I have a mechanism here to remove. Now I am releasing the air, I am allowing the atmospheric gas to enter into the tank. Okay. So in that case you can see that balloon will go back to the real size. I will repeat once again, all of you watch once again. I am going to operate the pump again. Focus on that balloon alone. Okay. Don't look anywhere else, look at the balloon. See again, I am going to open. You can see that balloon, see, balloon came to original volume. Okay. So let us see what exactly happened here. So in this case, let us go back to board and see what exactly happened here. Look here. In this room, you know the temperature we are maintaining, whatever is the atmospheric temperature, or in our room temperature maybe 20 degree, or if you are putting AC 20 degree or 30 degree, that will be the temperature in our room. So at that temperature, if you are maintaining the temperature constant and you are trying to reduce the pressure, see, once you are taking out air from the system, you know that you are basically reducing the pressure in the system. So once pressure goes down, something is happening to the volume. So this relation between at a constant temperature, when you are reducing the pressure, what is happening to volume, that particular thing, that behavior of volume when you are reducing the pressure at a constant temperature, this law or there is a relationship that is inversely connected. That means we are reducing the pressure. When you are sucking out air from the system, we are reducing the pressure, and as a result the volume is getting, you have seen that the balloon is increased, or the size is increasing, and as a result we can say there is a relationship, inverse relationship. Inverse relationship means, you know that if you are looking at two quantity, see, look here, you are considering pressure, okay, you are considering pressure and the proportionality you are trying to observe. So what happened here, when you reduce the pressure, the volume of the balloon was going up. This is the most important part you have to understand. If you remember, see, I hope all of you will never forget about Boyles law after seeing this experiment. So when the pressure is reducing, volume is going up. Okay. Now this, we can say that these kind of relationships, some relationships are directly proportional. That means once one quantity increases, other quantity also increases. For example, you know that F is equal to ma, or F is equal to kx minus kx, the spring equation. The more the displacement, you know that more force will be there, more restoring force will be there in the spring. So this, we call it, you know, force is proportional to the displacement of the spring, or the stretching of spring, or the force is directly proportional. So here you can say that is inversely proportional, or we can say P proportional to 1 by V. Okay. Again, you know, this relationship, if you are trying, see, the P, we can say that P proportional to V, or we can say another way we can write down this P into V will be a constant. So this way also we can write down, because you know, in order to replace the proportionality constant, we have to use a constant. So P, we can multiply, cross multiply, PV is equal to constant. This particular relation is called Boyles law. Now if you are plotting, see, in this case if you are plotting this relationship, you know that if you are plotting 1 by x, see, f of x is equal to 1 by x, you know that if you are plotting this is not a linear curve. Okay. So this is actually a different type of curve. If you are plotting that, you can see that this graph will be something like this. You can try this in any plotting software, you can go and check. So there will be an inverse relationship. So that is why we are getting graph like this. Remember here T1, any particular, right now we are focusing on one particular temperature. In the room we are assuming that the temperature is constant. So in that case T1 is the temperature. At that particular temperature, you can see that as you reduce the pressure, here you are reducing the pressure, and what is happening? The volume is increasing. This physical phenomenon is called Boyles law, or this is summarized as Boyles law. Okay. So pressure is inversely proportional to volume. I hope all of you understood, and we will do one thing. If anybody have any doubt, we will give you some time at the end. You can ask your doubts so that we will clarify that. Definitely we will clarify. And in between any doubt is there, you can post your comments in the chat box so that we will be able to reply later also. We can identify, or you registered, your number is with us. If you want, we can communicate with you later. You can drop all your comments, whatever doubt coming, you post there, okay. So entire chat will be recorded, we can reply on that, okay. So this law, this particular law is called Boyles law. I hope all of you understood the concept thoroughly, okay. Now let us go to next law. See, few 2-3 gas laws are there. We are going to discuss all of them today, and wherever possible we will show you the demonstrations. Otherwise we will show some animations and we will go back to the ideal gas relationships, okay. Now the second one is Charles law. See, this is a relationship between volume and temperature. I hope all of you might have studied already volume versus temperature. What exactly happened? Volume, if you are increasing temperature, what happens to the volume? That is what we are going to discuss. Now, before going to that, again I will show you one experiment so that you will understand what exactly we are discussing. Now remember, before going to this, we are going to demonstrate a system where pressure is constant. Pressure is constant means, you know, at that condition you are, see, if a system is expanding, or I'll do one thing, see, we'll first do the experiment, then I will explain what do you mean by the constant pressure conditions, okay. Let me set up the experiment setup, and all of you listen carefully. So all of you look here, I have a burner here, okay. Here is a butane burner, and can see it's a tent burner. We can have a like our cooking gas, you can burn the system, and we have a container. See, container, you know that, see, when you are at a normal temperature, certain volume will be there, and the inside pressure will be atmospheric pressure. We are not changing that quantity now, okay. Now in the system, what I am going to do is, I have to show you that what happens if I am increasing temperature. If I am increasing temperature, I have to show you that the volume is going to change. So that particular concept I am going to demonstrate. All of you listen properly, like focus here and see, try to see what all change is happening when I am performing the experiment, okay. So here I told you this is an empty can, nothing is there inside. It's like a magic show, right? So it's not exactly magic show, a lot of concepts are there inside, okay. So here I have a balloon. I am going to connect this balloon to the opening. This opening I am going to cover with balloon. Okay. Now we have covered this part with the balloon. We can see that. See, like this I am covering. Now I am going to switch on the burner. So you may not be able to see the flame clearly because it's a very light flame, blue color flame, because it's butane. Red color we cannot see. I hope all of you can see some flame. It's difficult to visualize, okay. It's difficult to visualize. Anyway, I'll show you. See, what I'm going to do is, I'm going to increase the temperature of gas inside. So already you know that there is gas inside, and certain amount of volume is trapped inside, and now I'm going to heat it, okay. So once I heat it, you look at the balloon, what exactly is happening to the balloon, you focus on that, okay. See, you can see that the balloon's volume is increasing, okay. Yeah, see. So that shows that when I'm heating, when I'm changing the temperature, you can see that it will stay there for some time till the air cools down, the volume will shrink automatically. After some time you can see that the volume will shrink. So what exactly is happening here? Look again, here we were discussing about increasing temperature of the system. So this is called Charles law, that relationship is called Charles law. So here you can see the temperature, we are discussing about temperature. So we are heating, when you are heating you using a burner, you know that we are raising the temperature of the gas inside. So what is happening? Basically the expansion will happen and the volume is changing, and pressure we are maintaining constant. That you have to understand, it's a very important concept. Process can happen at constant volume, process can happen at constant pressure, okay. So yeah, so we can say that, see here the pressure we are maintaining, at a particular pressure we are doing the experiment. That means even if you are covering this system, since you are allowing the system to expand, the pressure inside the system will remain constant. That is the main idea you have to keep in mind. So that is why we are saying, suppose one more case is there. If you are completely closing this, you are preventing the system to avoid any further expansion. That means, yeah, sure, no, it will take some, yeah. Anyway, I will show you, let it cool down, I will show you the experiment once again. Please wait for some time because right now the air is cold. Let us remove this. Yeah, I will show you, once I explain this, I will show you once again so that you can see the system clearly. So here what happens is, when you are, I told you the pressure is constant. See, if you are allowing the system to expand, as you are heating, see, the pressure will not change because you know you are allowing the system to expand. So pressure will not change in the case. So you can see that when you are raising the temperature, you have seen the volume is changing. So volume of the system is changing and pressure is maintained at constant. That means T is directly proportional to V. So this relationship is called Charles' law. Again, we can see that this is happening at constant pressure. It's a very, very important concept. The previous one was at constant temperature, the pressure was inversely proportional to volume. Here at constant pressure, the temperature is proportional to volume. More temperature, more volume. So that is what the Charles' law says. Okay, I will show you once again. All of you listen. Let us see what happened in this case. If anybody missed this experiment, you can see once again. I am covering the cover with a balloon. See, careful, focus on the balloon. Yeah, enough. It may burst. If you continue to heat, it may burst. Okay. So you can see that balloon size is increasing. So air is basically expanding. So this law is called Charles' law. Okay. So let us go back to the board. Oh, sorry. Okay. So one more law is there, Gay-Lussac's law. See, this one we are not demonstrating, probably in the next class we will be showing that, but I will show you an animation. Okay. So Gay-Lussac law, in the same situation, temperature versus pressure. So if you are changing the temperature, what happened to the pressure? So basically you have to understand that particular situation. See, you can have a container. You close it. Assume that in this system itself, you close it completely. Okay. In this particular system, if you are closing rigidly, that means you are putting a cap on top of that, then the system is closed. Okay. And in such a system, if you are increasing temperature, previously I told you, in the previous system we were connecting, maybe I will show you here itself, I will show you. So a balloon you are connecting, okay. So this part was open and you are connecting a balloon here, like this. So whatever air is there or in this system, when you are heating up, it is expanding and you know that the pressure remain constant and the volume is changing. So that is what happened in the Charles' law case. Now we are closing this part, we are completely closing. If you completely close this portion, what happens? You know that region, you can say that the pressure inside the system, the volume is trapped. You can say that the volume, there is no option, there is no room for expansion. So it will not allow any expansion. As a result, you know, the pressure goes up. That law is called Gay-Lussac's law. Okay. So the pressure versus temperature versus pressure you are plotting. I will show you an animation. Let us go back to the computer. All of you can see, I hope all of you can see the system. See this, here I have a tank. So this tank is completely closed. Okay. Now I can pump some air into the system. So I am pumping some air into the system. See, here I can pump. You can see that I am pumping certain amount of molecules to the system. Okay. So the temperature we are maintaining, some temperature is there. Say here is given 300 Kelvin is there now. Okay. Basically room temperature, we can say that 273 is 0 degree and 300 means around 25 degree or 27 degrees, that much will be there. Now if I am increasing, so in this enclosed container, if I am increasing temperature, I have a provision here to increase the temperature. If I increase the temperature, you have to look at the pressure gauge. See, here you can see there is a pressure gauge. So in the pressure gauge, what exactly is happening? You focus on that. Pressure, I hope all of you know the concept of pressure. Pressure is force per unit area. I am under the assumption I am taking this. I hope all of you studied properties of matter. If anybody have doubt, please ask that. Okay. So you can see that here you can see the pressure. You look at the value of pressure. So here I am increasing the temperature. So what will happen if I increase the temperature? So you can look at the temperature first. Look at the reading. See, is up to 600 Kelvin. You see the pressure is keep on going up. You can see that pressure is increasing. See, this simulation is not just a video. It's exactly the code behind this simulation is exactly following that Gay-Lussac's law. Okay, keep that in mind. It's not just a simulation or a video graphic or some. It's not like a cartoon. The entire system is encoded, or the code behind the system is exactly following that Gay-Lussac's law. So here, if I am reducing, you can see if I am reducing cooling down, you can see the pressure will come down. That means the temperature is proportional to pressure. More temperature, more pressure at constant volume. You are not able to, you are not changing because the volume is not, the confinement is there, and because of that, rigid boundary will be there. As a result, expansion for the gas is not possible. So that is what happening here. So here, cooling down, you can see the pressure is coming to lower value. Okay, so this law is called Gay-Lussac's law. Okay, it's very, very interesting. Probably in the next class we'll be showing this experiment as well. Okay, then you can see that. So if you are in this case, you have to close this, and when you close this and connect to a pressure gauge, you can see that if you are heating, the pressure will go up. Okay, so look here again. Let us go see the graph. So I told you, at constant volume, we are enclosing, we are constraining the boundaries, and as a result, if you are increasing the temperature, the pressure will go up. So again, we are getting a relationship, temperature proportion to pressure. In the previous case, we have seen that temperature proportion to volume at constant pressure. So this one, here the temperature is proportion to pressure at constant volume. Okay, that is the idea. Here it is constant pressure, T proportion to V, other is constant volume, T proportion to P. That is the difference between Charles' law and Gay-Lussac's law. I hope all of you understood these three laws thoroughly. Now, one more interesting thing is there. So that is very critical in the sense is applicable only in certain conditions. See, Avogadro's law. See, Avogadro's law says that is very interesting and important, and it was neglected for almost 100 years. It was neglected after his proposal, and later one scientist brought again a systematic analysis in chemistry got formulated, and people started using this law. So here it says that you can see that on the y-axis we are plotting volume per mole. Okay. On the x-axis is moles. I hope all of you by this time in basic concept of chemistry you are studying the concept of mole. Mole concept already know. See, mole in equal volume of all gas. The first I will tell you the Avogadro's law. Equal volume of all gases, are having same number of molecules. For example, if you are taking exactly, if you are saying at STP, we have to say that STP, standard temperature and pressure. STP, that 0 degree and atmospheric pressure is called STP. So if you are maintaining STP, if you are maintaining 1 mole of gas, okay, 1 mole of gas if you are maintaining, that will occupy 22.4 liter. This condition. So in that case, that 1 mole means Avogadro number, 1 Avogadro number of particles. So Avogadro number, all of you know that, you studied. Avogadro number is, that, see, this quantity, this much molecules. If you have this much molecules of a species, for example, oxygen molecule, if you are taking oxygen molecule, this much, if your sample is having this much O2 molecules, then we can say is 1 mole, we can say. So 1 mole of a system, 1 mole of a species having 6.022 into 10 to the power 23 molecules will be there, or this much molecules per mole. That is the idea of Avogadro number. Let us go back to the previous slide. You can see that. See, here is saying if moles are increasing, you can see all here you can say V by N is a constant. So V by N is a constant means equal volume of all gases and at same conditions will be having same number of moles, same number of molecules. That is the idea behind Avogadro law. So we have discussed all four. See, Boyles law we discussed, then Charles law, Gay-Lussac's law, Avogadro's law. See, now we are going to combine all the equations. You know that certain quantities are coming again and again. See, pressure is coming, volume is coming. We are using multiple times at different locations, different situation. We are maintaining one as constant, one as fixed. So we are trying to understand different situation. Now we are trying to combine all these things. And one more thing, this is not applicable everywhere. It's actually an empirical law. Again, in the last session I discussed about empirical system. Empirical means based on the experiments. If you are observing, find out certain kind of relationships, that is called empirical relationships. Okay. Anyway, this is an experimentally observed and based on the definition of Avogadro. That is actually a standard. See, you may wonder that how this number came. So if you are really curious, you can explore the details, how this Avogadro number, there's a relationship between one constant called Boltzmann constant. So we are going to discuss today about Boltzmann constant. So this is actually some standards we are setting to systematically study the species or the chemical, what is happening to the number of molecules. So these are standards. So based on that only we are saying at HCP, 1 mole will occupy this much space, and if you are taking certain volume, you can identify the number of moles, or simply in this case, you know, if you are taking same number of same volume of, for example, in one container you are having nitrogen, another containing O2. Assume that both are same volume. So then says that if it is same volume, then same number of moles, same number of molecules will be there in that system. That is called Avogadro law basically. Now, see, now the important things comes. See, we are discussing all these concepts in the case of ideal gas. So we have to understand what is ideal gas. We are going to that in a shortly we'll be visiting that what exactly is ideal gas. Now we are trying to combine all these concepts. So if you are trying, see today the concept, the idea behind today's session is you have to understand what are the gas laws, how to combine all these things together, and how to write down the ideal gas equation, what you mean by ideal gas equation, at least that particular concept. See, all these 4 laws, you have to, not 5 laws, I think, see Charles law, Boyles law, then Gay-Lussac, Avogadro, sorry, 4 laws you have to thoroughly understand. So you should be able to do problems based on that. Okay, that is the sole purpose of today's session. Okay, keep that in mind. We are not going to explore so many things today. Only this much concept should be thorough in your mind. So now you can see that if you are combining all these things together, it's very interesting. All of you listen with your complete focus here. You can see that, see, we are combining Gay-Lussac, Boyles, Charles, then Avogadro also. See, Avogadro also we are combining. If you are combining all those laws, we will get a particular equation. So you can see that, see, P, pressure is there, temperature. So PV is a constant. What is that? PV is a constant. You can see that. See, in the color you can see, you can match the color. So it's given that blue color. This part is blue color, and this is nothing but Boyles law. You can see again Charles law. See, here you can say Charles law. So this is Charles law. V by T is a constant because you know we saw that V proportion to T. Okay, that is Charles law. So here we can write down V by T is a constant. Okay, that is a statement for mathematical statement for Charles law. So this part is constant. Now again here one more thing, the Avogadro law, P by N is constant. So that, sorry, V by N is constant. So you can see Avogadro law, this is Avogadro, V by N is constant. So we are combining all the 4 cases, we are trying to get a single equation, we are trying to make a single constant. So if you are dividing for any system, if you are dividing the pressure of the system, volume and temperature and number of molecules, remember this is not moles, this is the total number of molecules in the system. Okay, N is the total number of molecules, usually small n is used for moles. I hope all of you are thorough about that. Small, what is the definition of small n? Small n is nothing but the molecular mass divided by, sorry, the mass of the species in your hand divided by the molecular mass of the system will give you the number of moles. Okay, and 1 mole means having 6.022 into 10 to the power 23 molecules will be there in 1 mole of a species. So that part already you studied in basic concepts in the first chapter in chemistry in +1. So here we are combining all the equations and we are getting a special constant. So we are getting a constant value, and that constant is called Boltzmann constant. Okay, So it's a very interesting and a lot of theory in statistical particle. So if you are going to details, you can see that there is a section called statistical mechanics, that is we are analyzing the motion of particle. That is a kind of microscopic analysis. In microscopic analysis, we'll be doing statistical quantities will be obtained. Statistical means you are considering a large number of particles. Still we are not doing microscopy. Large number of particle you are considering as individual particle, and you are trying to predict the behaviors based on statistical mechanics. In that, the Boltzmann constant is a very important system, okay, and in kinetic theory of gas is very important. So it's a constant, and its value is, Boltzmann constant usually written as Kb. Its value is 1.38 into 10 to the power minus 23 joule per Kelvin. Remember one more thing, in all these calculations temperature should be expressed in Kelvin. That is very important. See, usually students make mistakes in these calculations, and you have to use proper units. If you are using SI system, you have to follow only SI system. If you mix up units, you will end up in trouble. Even in SI system itself, sometimes you use kilojoule, kilogram, so that part also, question, usually the species will be given in gram, you have to convert into kilogram, so you have to be very careful, especially when you are doing ideal gas equations or these equations. So make sure that all the units, all the quantities you are using in a single unit system. That is very important, okay. So now if you are, this part is called ideal gas. We are combining all the laws, see all the 4 laws we are combining, and we are trying to make a single equation. So PV is equal to KBT, basically you are getting that, okay. So PV is equal to KB N into T, okay. So this is different. Usually you are studying another equation, I hope all of you know that, otherwise you listen. Usually we write PV is equal to nRT. So that is different. So this is actually the same way of expressing that equation, and just another method. So PV is equal to KB into N into T. Remember, this is not number of moles, this is the total number of molecules in the system. Total number of molecules, not moles. So usually for moles we use small n. So basically this equation is called ideal gas equation. So PV divided by NT, PV divided by ND is equal to a constant. If you are for any system, you consider any system, is called the state functions. These quantities are called state functions. In thermodynamics you will study, these are called state functions. State functions means the situation of that particular volume of particular species under consideration. So assume that you have certain, in this case in the balloon case, a certain amount of volume is enclosed in the balloon, that you can estimate the pressure, the volume, that if you are considering a piece of balloon, for example, in this you have seen that balloon is there. So in that case, certain volume will be there, certain pressure will be there, and a certain number of species will be there. That is atmospheric air we are pumping into the system. So the nitrogen 20%, then 28%, then oxygen will be there. So all together, lot of species are there, and certain amount of molecules will be there, and room temperature will be there. So these are called state functions. If you are dividing, even for a balloon, if you have a balloon here, for example. See, in this case, you can see this is a balloon. Inside, certain pressure will be there, certain volume will be there, all the species of air, so all together certain number of molecules will be there, and room temperature is is maintained at certain temperature. Then we can say that if you are dividing, if you are taking the ratio of that system, you are going to get a simple constant. That will be always constant. That is the beauty of this equation. So this says that if you are doing that, even for this balloon, if you are doing that calculation, you will get a single constant, and that value will be 1.38 into 10 to the power minus 23. This is the importance of physical constants. Is very interesting. So that is the idea behind ideal gas equation. Combining all the gas laws together, we are writing down a single equation, and we are getting one constant called Boltzmann constant. Boltzmann, okay. Boltzmann is B-O-L-T-Z-M-A-N-N, Boltzmann constant, okay. So now you are familiar with, I hope if it is covered in your school, or if you might have studied somewhere else, if you know that, you might have studied in another form, that is nothing but PV is equal to nRT, okay. Let us see that how to go to that, how to find out that equation. See, I am sure that you are thorough with this equation. Hopefully, if it is covered in your school or any other centers, this will be the equation for ideal gas. See, in this, again, pressure, volume, temperature is there. So here PV by T, okay. Here N is nothing but, I told you, this is the number of moles. N is nothing but the mass of system under consideration, of any species under consideration, divided by molecular mass of the system. That is called, for example, if you have 32 gram of oxygen, see, if you are taking 32 grams of oxygen, 32 divided by 32 is the molecular mass, that N will be equal to 1 mole of system. If you are taking 32 gram of oxygen, we can say that it is basically 1 mole of the system. So this is nothing but the mole, and R is nothing but, is called universal gas constant. So there is a relationship between R and N. So if you are, the previous equation if you are writing, you know that PV is equal to N into KB into T. This was the previous equation. See, if you are comparing these equations, you can see that directly if you are dividing, see, PV by T we can write down here, or we can say that NR is equal to KBT we can say, or you can nicely write down, see, if you are kindly finding out, see, KB, or I will write down both equations again, see, PV is equal to nRT. This is our first equation. And second equation, see, both are same. I am trying to show you that there is a relationship between universal gas constant and Boltzmann constant. This is capital N and this is nothing but KB and T. If you are taking a ratio, assume that if you are taking a ratio, you will get, so basically this part will cancel out, T will get cancelled out, so you will get basically 1 here, 1 will be equal to NR divided by capital N into KB you will get, okay. So you can see that R is nothing but, see here I can multiply like this, N into KB will be equal to N into R. Assume that you are considering 1 moles, okay. Assume 1 moles, then N is equal to 1. For explanation I am bringing that value. Assume N is equal to 1 mole, then you can say that N will be number of molecules will be equal to Avogadro number. So if N is equal to 1, you can say capital N will be equal to Avogadro number, Na. You can substitute that value here. So in that case you will get Na into Kb is equal to, Na into Kb will be equal to capital R will get. Or we can say that, see, KB is nothing but R divided by Na we can say. See, basically the gas constant per number of molecule divided by, this is the relationship between Avogadro number and universal gas constant R, okay. So this is the relationship, always keep this in mind. Usually we never discuss about this, only in the kinetic theory of gas Kb will be coming, the relationship between the velocity, the RMS velocity, we discuss when you are heating what happened to the velocity of the molecule. In that case only we are discussing this, but you know, if you are focusing on any entrance exams or competitive exams, you have to understand in terms of, you have to write in terms of Kb in terms of R and Avogadro number or number of molecules you have to write down. So basically this is the relationship between Kb and Boltzmann constant will be equal to universal gas constant divided by Na, and all of you keep in mind that usually the R, the value of R is very critical, in the sense the units you should be very careful, you have to use properly, you have to use only in SI units or whatever, you have to convert based on CGS or SI, all the quantities should be in that same system. Usually final answer will be wrong if you are not careful in that case. Be careful, that is the single point where you can make mistake. All of you put maximum effort to understand that whenever you are doing problems, okay. So let us come back to in SI unit, R value is also very important. 8.31 is a universal constant. 8.31 joule per Kelvin per mole will be the unit of universal gas constant. Sometimes we will write UGC, okay. Universal, like universal gravitation constant, this value is universal gas constant. I hope all of you understood the theory. This is the entire theory behind ideal gas. It's a small section in the chapter. You can get questions based on that. If you are thorough in this portion, definitely you will be able to go to next, you know, adiabatic process, isothermal process, all the work done. A lot of things are coming in the thermodynamics chapter. So if you are thorough in this equation, then that part will be really easy, okay. So now See, there is two things, one is real gas and one is ideal gas. So real gas, the name itself says that real gas. So what exactly is around us, that is real gas, that is not actually ideal. So two important assumptions are there that you have to understand. What exactly you mean by ideal gas? So that is important. See, ideal gas, we are assuming that they do not attract or repel each other. That is the important point. Okay. So ideal gas, we are assuming that they are not interacting each other. So as a result, we can say that they are individual particles and they don't have any, actually that is not the case. Molecules when it comes close can attract or repel depend upon the charge or depend upon the shape. Lot of things are there, it can happen. So in reality that is not happening. That happening in the sense, it may attract or repel, that is possible, depend upon the charge levels is possible, or any other property based on any other case it can happen. So in ideal gas, when we talk about ideal gas, we are neglecting the fact that they attract or repel. We are assuming that they are not attracting or repelling, and basically they are not interacting each other, and only elastic collision is happening between them. Elastic collision means, if two particles are there, there is no loss of energy, there is no loss of frictional energy. Frictional energy means you have to understand that is internal friction. See, if two particles are colliding, if the shape is changing, certain amount of energy will be lost inside if friction is there because of the internal friction inside the particle. So if that is the case, that is called inelastic collision. So in this case, elastic collision means if you are moving with a velocity, that momentum will be completely conserved, energy will be conserved, and if there is no loss of energy, then we can say that if some amount of friction is there, then heat energy will be generated when you are hitting particle. So if that is not happening, we call it elastic, perfectly elastic collision. So we are assuming that in the ideal gas case, if you are calling a gas ideal, then we are assuming the fact that they are not interacting each other, and only interaction is the collision happening, that is elastic collision. So very, very important concept. Okay. Now the second is the molecule themselves take up no volume. Basically we are considering each and every particle as point particle and assuming that they are not taking considerable volume. So that's also important. In real life that is not the case, in real gas that is not the case. So completely opposite will be the reality. Reality will be, the particle will be interacting each other, and at the same time inelastic collision is possible. So that is the reality based on the first statement. Based on the second statement, definitely the particles will be occupying certain amount of space. So this is the difference between ideal gas and real gas. The equation we discuss is applicable for ideal gas. So this is an ideal case, but it's applicable for most of the situation, and major calculations can be done. If you are trying to estimate, for example, I show you, like I shown you the balloon. So in this case, if you are trying to find out based on the given volume or given temperature, if you want to find out the pressure inside, you can use ideal gas equation. But in reality, slightly some correction you have to do. The reality value will be different. That is the idea behind ideal gas equation and real life, like real gas case. So I hope all of you understood the complete theory from this section. So we discussed, I will once again revise. After this, we'll be doing some problems, and before that I will quickly revise once. Yeah, so here first one is Boyles law. Boyles law is saying that pressure proportion to 1 by V. In some problems you have to directly use Boyles law alone. We are no need to use any temperature or other thing, because we are assuming that temperature is constant. If a problem is like that, then you have to use only this relation, PV is equal to constant. You will be able to solve the problem. So this is based on the Boyles law. Charles law, see, volume versus temperature if you are plotting. So temperature proportion to volume at constant pressure, that is called Charles law. Then next one, see, Gay-Lussac law, the pressure versus temperature. If you are increasing temperature, the pressure will be increasing at constant volume. Then fourth one, Avogadro law. See, if you are taking equal volume of different gases or any different gases but equal volume, at STP it will be having same number of molecules. And one more important thing, STP is nothing but 0 degrees Celsius and 1 atmospheric pressure is called STP, and 1 mole will be occupying 22 liters of volume. That factor you have to keep in mind. And 1 mole means 1 Avogadro number of particles will be there. That is a standard we selected and we are following that. Okay, there are historical reasons behind that for particular the choice of that number. We can explore that. You can understand if you go to the history of chemistry, you can understand that why we are choosing that particular value. Anyway, that is out of our scope. I am not going to that details. So here this is important, Avogadro number. I hope all of you are thorough by this time, since you studied in the basic concepts of chemistry. So 6.02 into 10 to the power 23 molecules, per, if you are taking 1 mole of gas, this much molecules will be there. That is the idea. Then we are combining all these equations and we are introducing a constant called, we are calling it Boltzmann constant, the pressure of a system, then volume of the system, then we are dividing that quantity by T, temperature, and the total number of molecules, then you are getting a constant called Boltzmann constant. This equation is called ideal gas equation. You can express in terms of one more way, like in terms of a universal gas constant we can explain that equation. And again, before going to that, Kb we discussed 1.38 into 10 to the power 23, joule per Kelvin is the unit. And always remember, Kelvin will be used in all calculations, degree Celsius is not, like you are using degree and radian. So here in all SI unit calculations you have to use Kelvin, and all degree calculation you have to use radians. You know that, you already know that part. So then one more way to write is PV, anyway this one we discussed already. So PV is equal to nRT is another way, and where R is nothing but universal gas constant, 8.31 into this much joule per kilogram per mole is, sorry, joule per Kelvin per mole is a unit, and that is called universal gas constant. And there is a relationship between universal gas constant and Boltzmann constant. You can write down both equation, you can divide it, okay, you can show that if n is equal to 1, n will be equal to Na, or basically Boltzmann constant is nothing but R per total number of Avogadro number of molecules, or if the universal gas constant per or divided by, this is the relationship. This relationship is very useful in while doing problems, especially for JEE Advanced and all these kind of questions you can expect, okay. So this is the idea behind the relationship between Kb, the Boltzmann constant, and universal gas constants, okay. Yes, then we discussed about the ideal gas, the concept behind ideal gas, and real gas we discussed. I hope all of you know this. It's a theory part, and these are the important assumptions. You may get some assertion reason type question. So if you are previously AIMS type of question, now AIMS exam is not there, this kind of exam, and now we can expect the same in JEE Advanced. So a lot of assertion reason questions will be there. As you know, the problem with assertion reason questions, you should be really thorough in the concept, then only you will be able to do assertion reason type. Simple reading will not help you. So these kind of statements you should understand thoroughly, and you have to apply again, you have to understand, read again and do questions, similar questions, then only you will be thorough in that. So assertion reason type questions are really tough compared to normal numerical type. That you will understand. You attempt some problems, then you will realize that you will confuse, they will confuse by twisting the things, and these kind of statements you give importance and understand, especially in chemistry you have to give a lot of importance, okay. Fine. Now, yeah, so we'll be, see, I hope all of you might understand that how we are teaching. We are using active methods. Active learning methods means you are showing something to you, and you are trying to go back to the board and trying to explain what exactly you studied, what exactly you saw, and trying to connect with what all things happened in the surroundings, in your surroundings, so that you can directly connect what you're studying with your daily life. Okay, that is the idea. That will help you to read, and I told you, I'm repeating it, that will retain the concepts in you, and it will help you to really think yourself, so that the purpose is not just exam. You see, all of you are scoring properly in exams. We know that Indians are very notorious for that. The exam score will be perfect, but if you're asking something, they're completely blank. The once exam is over, they are not able to apply anything. Majority, I'm not saying that everybody, but some people will be there. They are trying to understand, but majority people, if you're looking at, you are not able to recollect what you studied in school, or you are not able to apply what you studied, and you are not able to think based on what you studied in school or based on the textbook. So that is a major problem. That's why we are working on that. We are trying to teach by showing these kind of activities, so that will be retain the concepts for a longer duration. And not only that, you can see in the complicated exams like JEE mains, if they're twisting something, if you know the concept thoroughly, it will be very easy. If you are by hurting and trying to do some exams, that is entirely different, and you may end up in suffering. You may fall in the trap in that question. Okay, so you may choose wrong option in that case. So here, when you are seeing something like this, you will be able to, some thinking process, naturally some thinking process is happening behind you in your mind at the background, so that you will be able to connect with all the concepts, and you will get a solid concept behind this. Okay, so that is the idea. So behind that is why we are focusing on these kind of methods, active learning methodology. We have a dedicated team for that. We are doing that. I hope all of you can feel even now itself, and we are developing a lot of things for entire chapters, entire concepts. We are wherever possible we are using experiments. Okay, fine. That is the idea. Now let us do one thing. See, this is a previous year medical question. It is 2004, it was that time NEET was not there. It is AI PMT question, and try to do this. It's a very simple question. You can even get these kind of questions for NEET. If you are a NEET aspirant, it's not a big deal. You understand the concept thoroughly, do certain level of problems, you can easily crack. You can get a very good score. So I'll do one thing. I'll give you 2 minutes time. I will explain the question. I'll give you 2 minutes time. All of you attempt, drop your comments in the chat box. I mean your answers in the comment box. Okay. Yeah, let us see the question. See, here you can see that the equation, see, we have to write down the equation of state. Equation of state, I told you, when you're taking a system, what is the pressure, what is the volume, what is the temperature, what is the number of molecules in that, that is called the state function, that is called state of the system, and that quantity is called state functions. So if you are changing one thing, it will be, they are interdependent and some quantity will be changing, that is called state function of that system. Now the equation of state for a 5 gram of oxygen, okay, at a pressure P and temperature T, when occupying volume V will be. It's a direct question, it's a direct application of equation, and try to do that, but you need some information for oxygen you have to understand. I'll give you 2 minutes time, all of you attempt, and please drop your comments. Yeah. Yeah, 2-3 people answered. Nabithanjali answered first. Congrats. Okay, great. It's a direct question anyway. Then Yagnesh, then Joshua. I think all these people answered. Everybody is getting it. It's a direct question. So look at this question. What is given here? See, 5 gram. So mass of the system is 5 gram. Is given. Mass is equal to 5 gram. You know that molecular mass, you need molecular mass of the oxygen in this case. See, O2, if you are taking molecular mass of O2, see, MO2 will be how much? 32 gram. That means if you are taking 1 mole of the system, it weighs 32 gram. That is the standard we are maintaining for O2. Okay, I mean based on the mole concept, that is why that is what we defined. Now, see, 32 gram will be the molecular mass, and mass of system will be 5 gram. You can find out number of moles. Number of moles is nothing but mass divided by molecular mass, that will be equal to 5 divided by 32. Both are in same system. So number of moles we obtained. Now we have to find out the state function. State equation we have to write down. See, is a direct question actually. So we can see that PV is equal to nRT, we can see. See here PV is equal to nRT, and you have to substitute and look at the option C. Basically this shows that PV is equal to 5 by 32 RT. Okay, that is the right answer. You can see the right answer is the first option. So this is the right answer. I hope all of you understood this, that these kind of direct questions you can get, but you need some information like this 32 gram you have to keep in mind. That is the idea. Anyway, it's a simple equation. I am not complicating because we studied only the gas law, but based on this, you know, some Mayer's relation will come, then adiabatic process. You can, if you have a thorough base on this subject, you can go to that details. Okay. Anyway, let us go to one more problem. Okay. Before going to that, you know, we wish to discuss something about this exam grid. Exam grid is our one of our software, like one of our exam platform. We can go and check examgrid.com. So where you can take a lot of online exam. You know, if you are practicing, we have a system there, and you can take your test. If you're a NEET aspirant or JEE aspirant, there will be separate questions for that. You can choose your own level, and I mean the difficulty level you can choose, and you can attempt questions, and you will get immediately the answers. The key will be, sorry, the score will be coming once you submit the exam. Score will be coming to your mobile, I mean SMS or email. Then you can track the progress. You can regularly do exams, and you can track the progress, and you can manage time. That is very important in competitive exams. You have to practice a lot of tests. Based on that, you will be scoring well. You know, basically you will be knowing all theory, but you know, in time you have to solve that. The time management or the calculation part you have to practice. That is the most, that the successful people are those who are putting effort to do the problem quickly in time. Okay, 1 minute you have to solve one problem. So for that, this platform is very good. We are making this, we are still developing this problem, like more questions are being added, and there is solution. Once you are submitting the exam, you will be getting solution, and you can go and browse, and you can find out solution of each and every question. Okay, fine. Go and check this examgrid.com. Okay, let us do one more problem. Okay, so here we have two vessels. I will explain again. I will give you 2 minutes. Try to answer quickly. See, two vessels separately contain two ideal gases A and B. Two species are there, and both at same temperature. Let it be T. And the pressure of A being twice that of B. So it's given that the pressure of A is equal to 2 times pressure of B. Okay. Now, under such conditions, the density of A is found to be 1.5. Rho density is represented by rho. So rho A is equal to 1.5 times of rho B. Now, the ratio of the molecular weight of A and B is, that is a question. What is the ratio of the molecular weight? The question is MA by MB. What is the answer? All of you try, and try to post your answer quickly, as quickly as possible. I'll give you 2 minutes time. Let us do that. Okay, please do and come back. Yeah, congrats. Said Muhammad did the correct answer. Thank you for that, for your quick effort. Congratulations. Let us see others. Please look at this. So how to solve this? We have to find out this particular ratio. Here, the given quantities, these are the given quantities. Now we have to do a small formulation here. You already know the ideal gas equation is PV is equal to nRT, you know. Okay. Now you already know that N is nothing but the mass of the species under consideration divided by the molecular mass of the system. Again, one more thing, density is involved in the system, so we have to bring in density somehow into the system. So density will be equal to mass by volume, mass of the species by volume of the species. Now you can do one thing, see from here you can take the equation for V. If you are taking the equation for V from there, let me maybe here itself we will do, okay. V, I will rub this part, I will write down this again. Okay, so here density we have to write down. So volume first we have to take. Volume will be is equal to how much will be there? nRT divided by P we can write down. So mass is, density will be equal to mass by volume. Mass divided by volume is nothing, we can write down nRT divided by P will come in the numerator. Now M we can write down. M is nothing but from here what it says. This implies that M will be equal to small n into capital M we can write down. So here we can replace the small m as rho will be equal to will be equal to n into m we can write down. N into m into P divided by n into RT we can write down. So from here we can cancel out this n will be cancel out, because when you are talking about density the number of molecule is not significant. We can see that this will be rho will be equal to m into P divided by R and T. See, this is the final expression. You can see that here given at the same temperature. So this is independent. R is anyway universal constant. So this is also a constant. So we can say that directly by looking at this, with this implies that the rho is proportional to molecular mass and pressure. So here the variation, so we have to identify the variation of molecular mass or the ratio of molecular mass we have to find out. If we have two systems like that, we can easily do the division we can do. For example, you can see that here, see for example rho A will be proportional to MA into PA. So we can do again rho B will be proportional to, MB, molecular mass of the B into pressure of B. Take the ratio, if you are doing that you will directly get the answer. So rho A, you already know the value rho A. So rho A by rho B you have, that will be equal to MA divided by MB into PA, PA divided by PB. Now you already know that, see what is the relationship, pressure of A is twice, given that PA is equal to 2 times PB, and one more thing is given, and rho A will be equal to 1.5 times rho B, that is given. So that values you substitute, that's all. So PA by PB we need, PA by PB is equal to 2. Okay, so here this implies that, here I will write down, this says that this ratio we need MA by MB, or we can write down this implies that MA by MB will be equal to, okay, see MA by MB will be equal to rho A by rho B into PB by PA, PB by PA. Okay, that says that rho A by rho B, how much is rho A by rho B? 1.5, or we can write down 3 by 2. Okay, then PB by PA, that is again 1 by 2. Okay, so answer will be 3 by 4. So that is gives you, that will give you 3 by 4. So 3 by 4 is the right answer. So this is the right answer. I hope all of you understood this. Okay, fine, let us go to next. One more question is there. We are going to wind up in 5 minutes. We will wind up the session. Please be patient. And just one more thing we want to share with you before going to the question. See, we have a separate wing for stress management and optimum performance. You may not know much about this. You know, usually people suffer a lot, while especially those who are attending board exam in that year, you will be suffering with a lot of pressure, lot of stress will be there, because you have to, everything you have to do in the last moment, so much issue will happen. So that time we have a special team to guide you, and trained psychiatrists and psychologists are there in our team. and they will be giving you right advice if you are suffering in such a situation. Okay, and not only that, and after the course, career guidance wing will be there. You will be getting right advice at right time, so that you can choose your career based on your passion, based on your aptitude. You can choose your career. We have a team for that. Will be helping you a lot for such things. Okay, so we wish to share these kind of services which we are providing at this time. Okay, anyway, just one more question. This is a JEE advanced question. You try to do this. It's a slightly not complicated, I cannot say complicated, but it's an advanced question. Try to understand, try to do the problem. Okay, so I will explain the question. With this, we are winding up the session. See, two non-reactive gases, monoatomic gases. Monoatomic means one molecule is there. Okay, monoatomic, for example, that argon is a monoatomic, radon is a monoatomic, like that, helium. So like that, monoatomic gas, ideal gas, how their atomic mass is in the ratio 2:3. Atomic mass is in the ratio 2:3. Then the ratio of the partial pressure when enclosed in a vessel kept at constant temperature is 4:3. Okay, the ratio of the partial pressure. See, what is partial pressure? That is an important thing. Partial pressure is nothing but, assume that in a balloon. See, you know that in this balloon, even argon is there, radon is there, krypton is there, oxygen is there, nitrogen, carbon dioxide, everything is there. So all together, certain pressure is there. See, how much partial pressure you have to understand properly. Partial pressure means if you are maintaining that particular gas under consideration, or the O2 you are considering, if you are giving entire volume and that particular temperature, how much will be the pressure? That is called partial pressure. Now this is a mixture. Listen, this is a mixture of gases. This contains a lot of species, and the partial pressure and the entire pressure is nothing but sum of the partial pressures, and that is what we are experiencing. And a particular species, how much will be the pressure if you are allowing only that species to occupy the entire volume at that particular temperature. That is called partial pressure. Dalton's law of partial pressure will be coming. Total pressure will be sum of the partial pressures. You have to go and revise that topic. Is a very important concept. So partial pressure of the gases are in the ratio of 4:3. The ratio of their density is, that is the question. We have to find out the ratio of the density. Again, I will give you 2 minutes. After this, we will be quickly winding up the session. Please be patient for 2-3 minutes more. So we are winding up. So try to do the answer. Yeah, congrats, many people answered. Okay, so thank you for your attempt. So I think more than 3 people answered. Yeah, good. Said, you are answering B, that is wrong. Okay, yeah, anyway, many people answer option D. Yeah, option D is the correct answer. Many people answered. Yeah, thank you. We cannot say who did first because many people simultaneously posted. Yeah, thank you, congrats anyway. So it's a question similar to the previous case, only you have to understand the partial pressure concept. That is the only thing you have to do here. See, again, PV is equal to MRT. You know that PV is equal to nRT, and you know that N is nothing but mass by molar mass. Okay, density is nothing but mass by volume. You will get a relationship if you are using density. If you can write down like this, density will be equal to, I'll use black color. Okay, density is equal to mass divided by volume is nothing but nRT, sorry, nRT. See, nRT divided by see volume I am replacing by P will come, and mass I am going to replace by Nr. So that rho will be equal to, rho I am going to substitute with N into M into P divided by N R T. So N will be cancelled out and you are getting the relationship directly. Rho will be equal to M into P divided by RT. So here in the case monoatomic is the ratio of the atomic masses are given. Assume that you are considering two systems, okay. First one is A, okay. Second one is B. So the ratio MA by MB is given, okay. MA by MB, that is given as how much? 2 by 3 is given, 2 by 3, okay. Similarly, one more thing is given, the partial pressure. Partial pressure is nothing but the individual pressure experience if you are expanding, if you are allowing that particular volume, particular molecule, particular species into that entire volume. So we can write down PA by PB, that is also given 4 by 3. So 4 by 3. So here you can write down. So rho A, okay, rho A by rho B if I am doing, you will get, how much you will get? MA by MB, then you know that PA by PB will be there if you are dividing that directly, okay. So MA by MB, just a moment. So divided by, sorry, this one I am dividing this with the, so one different, some mistake I made here, sorry for that. First you have to write down both equation, then you can divide. See, assume that this one is rho A, that MA and PA, and this one is at same temperature, see at constant temperature, and this part will be constant, or we can directly write down this portion like P proportion to rho proportion to M into A we can write down. So rho A will be proportional to MA into PA we can write down. So here we can write down rho B will be proportional to MB into PB, okay. So here same as the previous question, but only thing you have to understand the concept of partial pressure, okay. Now if I am dividing this, how much you will get? You have to find out finally the ratio of the density. So this quantity we need, so rho A by rho B will be equal to MA by MB into PA divided by PB. That will be equal to MA by MB is already 2 by 3, okay. And other one is, how much was that? 4 by 3, sorry I missed this, 4 by 3, okay. So 4 by 3, and final answer will be 8 by 9 will be the right answer, okay. So answer option, right option is 8 by 9. In fact, many people tried this, many people got right answer, congratulations. So we are winding up. I hope all of you enjoyed the session, and one more system is there. We have a learning management system, so where all the videos or all the sessions will be recorded. If it is online, or everything will be recorded, you will be getting a login, and anytime, even if you are missing some sessions, you can go back and watch the videos. You can basically is a benefit of online session. It is completely absent in offline sessions, and you will be able to view all the missed classes and all. And not only that, lot of DPB daily practice questions will be uploaded, and you can test before every day. Small test will be there, so you can continuously evaluate your performance. So after all, all the data will be accumulated at the back end, and you can see entire progress. We can see it's completely a professional management software, management in the sense, class management software, and it's UNS e-learning app. It's already available in Android. You can go and browse, and web version is also available, and you can try that. It's completely a organized system, so you can completely manage your performance, okay. So these are the details. I hope all of you understood about all of you understood about our methods, how we are teaching. If anybody is interested, you can go back to, you can come to our center. We have two centers, one in Velacheri. Velacheri is in our Sitapati Nagar, and another one is Nanganallur, and you can contact any of our counselors, and you can get more information. If you want, you can fix a direct meeting so that you can share more information about how our teaching methods, and you can interact in a better fashion. And thank you very much for your attention, and we'll see somewhere, and if you will join, or you'll see somewhere else. Okay, thank you very much. Bye. Good night.